These are continuing the notes we did on Friday, which ended with the beginning of number 20. Yes? Yes, that's also number 20. And as we do continue with number 20, yes?
This is recovery method.
These are recovery methods for natural gas. We did petroleum already, not natural gas. But as all of you are taking these notes, I'll need to distract you, please, to make sure everybody has a solar house group. Because this room holds 35 people, we must have one odd-size group, but only one. Raise your hand if you are currently in a group of 3. Currently in a group of 3. Then raise your hand if you are not in a group of 3. In any way, not in a group of 3. Now stand up if you are not in a group of 3. Stand up if you are not in any group of 3. Apparently, Julia, you are. Please sit down. Do you need me to make you into groups, or can you make... That's one? Thank you. Now, what about these dudes? Do they have a third? Cool. You can sit. Cool. Can you guys be a group of 2? Is that okay? You guys not like each other? You are friends.
We can have a group of 4 and I can be
A group of 1? No. Because there's only one odd-sized group. I know you want to be a group of 4, but no, you cannot. Because there will only be one odd-sized group. They're a group of 2. You guys cool? Wicked. Are there any questions about grouping?
Is anyone not here though?
What's that?
Some people might not be here.
No, everybody's here. This is everyone.
Yeah.
So thank you. We now have our solar house model groups. I hope everybody understands. Either all my classes break up into groups of 3. If there's one extra person, that would mean one group of 4. If there are 2 extra people, that would be one group of 2. And then if there were 3 extra people, that would be another group of 3. So we always have just one odd-sized group if we have odd-sized groups. Had there been less people, I have no problem with you being a group of 4, but that would have made 2 odd-sized groups. But it's just too hectic, because then kids always complain that, like, oh, Hannah didn't do anything, this is horrible, Spartan. Okay. Your solar house your solar house plans are due next Tuesday, which is the 4th of February. Next Tuesday. Remember, you will need, number 1, a 3-dimensional color view of your house from the street in poster form. Number 2, 2-dimensional black and white construction schematics in poster form of the top view, back view, front view, side view, or views. And you will need, third, an 8 by 11 sheet of paper, which is a key that numbers, please look on. 7 of these 8 passive solar principles. 7 of the 8. And wherever they show up in the drawings, they would have the corresponding number. So in the top view and maybe the back view, you would say number 3, and then on the key, number 3 is the green roof or something. Does that make sense to everybody? Are there any questions about what's due next Tuesday? Yes?
When
I haven't decided yet. Thanks for asking, but I don't know. Probably the 3rd or the 5th. The 5th, probably. 5th, maybe the 6th of February. I believe it is the 7th of February. Because it's a big old unit with a lot of content. Are there any other questions? One last thing I'd like to remind you about. If they're empty, Alexa, we do that triple stack thing where it's one clamshell, the other clamshell, and inside a third. I want to remind everybody that you can get 1 extra credit point if you make an interesting design that is either an unusual shape or an unusual application of these principles. Yes?
Are there any of these houses that need
that? I think this one got a point because of a very good use of thermodynamics. This one got a point because of the shape, which at the time was kind of unique. This one got a point because of the convection currents. I think I might have thrown them a bone because it was just such a beautiful model, but not for the plant. Actually, these guys got a point for the model, and another one of these got a point for the model, but I can't remember which one. Okay. Your energy use inventory is due tomorrow. That's the worksheet you did with the information from your energy bills. If you didn't have your own energy bills, you were instructed to get information from another student. The energy use inventory is due tomorrow. Are there any questions about the energy use inventory? Yes?
Is the PDF on EDU?
I believe so. You could check right now so we could settle that. Anybody else? Graham will let us know if the PDF is on EDU. If not, there might be hard copies in the back. William, can you check to see if there are energy use inventories in the back? So Graham will let us know if they're on the internet. Any other questions before we get into the nitty-gritty? What? For the models? It'll be sometime in March. About 4 weeks after the plans. All right. So let's get back to natural gas. Last Friday we talked about how natural gas is a relatively new energy source, correct? Because it's been kind of hard to do the plumbing back in the day, so nowadays we can do that. Did we talk about that? Did we talk about why natural gas is clean? No. At the beginning of number 20, what? Did we talk about what natural gas is made of? So you wrote it down, but we didn't talk about it? Here we go. When natural gas comes out of the ground, it is a blend of the 4 natural gases. Those are short hydrocarbon chains.
There, the PDF's on.
Thank you. Graham says the PDF of the energy use inventory is on EDU if you need another copy. The 4 natural gases, please look up. Single carbon, double carbon, 3 carbons, and 4 carbons. With all the other sites clogged with hydrogen, those are the 4 natural gases. Methane, ethane, propane, and butane. And please note that when it comes out of the ground, there are other gases mixed in. Oxygen, nitrogen, CO2, some amounts of hydrogen sulfide, the rotten egg smell. When you get that stuff out of the ground, you squeeze it, and by compressing it, the gases will turn into a liquid at a different amount of pressure. So you squeeze it just enough to make these liquid, then you release all the bubbles of other stuff, then you decompress it, and now you have pure natural gas. Almost all of the natural gas is methane. At least 3/4 of the natural gas is methane. The last quarter is a mix of ethane, propane, and butane. Please look up. This is 70 to 90% of all natural gas. Are there any questions about this? Yes?
You said it gets, it's like a blend of mixes. Do you just mean the 4 natural gases?
Yes.
Okay.
When it comes out of the ground, there are also other gases.
Yeah.
So it's those 4 blend plus other things. Yeah, those are usually refined out. You're left with what's called mixed natural gas. You can further refine it into each of those separate parts. So like the butane, they take away for like liquid fuels, and then the propane, they take away for the propane infrastructure. Ethane, I believe they use a lot for commercial chemistry. Will?
So I don't know about methane, but I know butane like is drops. I know it's like super low temperature or something. How come it like falls down to the floor? Like, is there a reason why? Is it heavier than methane?
I reckon it must be because there's more stuff in the molecule.
Yeah.
I don't know much else. It doesn't rise on its own it doesn't go into the atmosphere. It sits at ground level.
Yeah.
That's cool. I didn't know that. Yes.
When they harvest something like butane or propane, they have to they obviously refine it to put it into like a can to give to us, right? It's not like, or is it just like comes out of the ground and can be put into like that?
No, it has to be refined before it comes to you. It's purified.
But does it change like consistency much or anything, or is it just like pretty much?
It's just it's purified. I share the bed with my daughter, and her hair gets stuck in my beard. Yes.
So you said they compress it, and then they decompress it?
Yes.
After decompressing it, is it still liquid? Or is it...
No. Anybody else? Yes.
In the tanks for cars, is it liquid or gas?
In a natural gas car, it is pressurized into liquid form so you can carry more. Anybody else? Now perhaps you've heard that natural gas is a clean burning fuel. But we got to talk about that a little bit. Because it is, but it's not. Sort of right, sort of wrong. You need to know what the major impurities are of fossil fuels. You should write this down. They are NPS, nitrogen, phosphorus, and sulfur. Like National Park Service, nitrogen, phosphorus, and sulfur. And to a lesser degree, a variety of heavy metals. Those are the impurities you often find in fossil fuels. Because keep in mind, if we're going to take Kyla and compress her into a lump of coal, the hydrocarbons become the energy, but there are other elements in her body. She has nitrogen in all of her proteins, and some of those will get stuck to the hydrocarbon. She has phosphorus in her proteins, and some of those will get stuck to the hydrocarbons. There are sulfur compounds in her proteins that will get clumped onto her hydrocarbons. These are what we call impurities. Not Kyla herself, I mean. Nitrogen, phosphorus, and so on. Now, in petroleum, these are very common. In natural gas, these do not exist. And it's very important that you understand this one very odd distinction. Those impurities can, yes, they can chemically bond with natural gas, but when they do, it stops being a gas. Turns into liquid or it turns into solid. So those impurities that you listed are simply not found in natural gas because when they are in the deposit, they just don't make a gas. However, I told you that natural gas is clean in sense of impurities. Yes, it is, but not in another sense. Can anybody think of the one type of pollution that's unavoidable? Right. She said carbon. Someone said carbon. She said carbon. So I'm glad you're going to remember that whatever it is you lit on fire, carbon is the same proportion to energy, whatever is the energy source. So if you burn petroleum to heat 1,000 gallons of water, you'll get the same CO2 that you would if you burned coal to heat the same 1,000 gallons of water. Thank you, easier. And you would get the same CO2 if you burned wood for the same amount of energy. And if you want to get that energy out of burning paper, you'll get the same CO2. And if you want to get that same amount of energy out of burning your mom, you'll get the same CO2. And you can burn babies, and you can burn spare tires, and you can burn plastic bottles. And if you're going to get the same energy, you'll get the same CO2. Because those carbon bonds give you the energy, the same amount of carbon is required for the same amount of energy, so with the same amount of carbon, you'll get the same amount of CO2. Yeah?
So the places where like different efficiencies occur is just in the processes that you can get out of. Like coal might be like more or less efficient than natural gas. That's not because of the carbon bonds, because of the processes we have.
Now, technically there are other parts of that thermal efficiency that are not captured in the conversation I've had with you so far. So for example, the difference in burning temperatures of those other impurities can affect the overall efficiency of the fuel. Coal burns a little cooler than natural gas because you've got all that other crap that doesn't catch on fire as well. Petroleum, I imagine, must also have differences, but I don't know what those are. You know, lighting your mom on fire, maybe the fingernails don't burn as cleanly, and so that would lower the temperature a little bit. I don't know, man. There are other efficiencies in the question, but as far as the energy captured in carbon bonds, you'll get the same amount of energy out of carbon bonds per unit of CO2 coming out, no matter what your fuel is. So when you're burning petroleum, you're burning natural gas, you're burning coal, the amount of energy is almost exactly the same per unit of CO2. It's not cleaner in that sense. But everybody knows, right? If you burn car tires, you get that big toxic cloud of black smoke. Okay, those are all impurities. Particulate impurities, other gases, miscellaneous pollutants. Gas doesn't have any of that. But as far as global warming is concerned, it makes no difference which one you're burning. As far as CO2 goes, same amount of heat, same amount of CO2. That's the end of the conversation. Questions about this? No? Remember my analogy from Friday, please. Joe Schmo Public thinks that petroleum is underground in this giant vault of petroleum. But you know better, right? How is that petroleum found underground? In rocks, that's right. So now imagine the challenge of getting natural gas out of the ground. When you do primary extraction, you crack the ground and the gas just rises out on its own. You got to capture that somehow. Then you can get into secondary extraction where you go and you pump water into the ground and that squeezes some gas out of the other wells. So you go and you pump the water in one place and the gas will bubble out in the other wells. Secondary extraction. But a bunch of geniuses figured out this other thing called fracking, which, remember, is tertiary extraction but for natural gas. Primary and secondary are the same, but this is a unique type of tertiary extraction for natural gas. And FYI, just so you know, you can get a little petroleum out of that. Like globally, the net volume of fracking, about 2% of the production is petroleum. About 98% is natural gas. You get a little bit of petroleum out of it, but not much. As you saw, there's a lot of this in the ground. Getting it out is really tricky. And there are some tough political decisions to make about fracking. I have a really handy diagram. The well on the right is squeezing water into the ground. But I'd like everybody to visualize this, please. I take a pipe. I hammer it into the ground. And now I squeeze water into it until bubbles come out of another pipe. And now what? If I just, this is like full of water, it's just water. Imagine if I could fill the pipe with water, add chemicals and sand. We'll come back to that. Remember that I said chemicals and sand are in the water? At the top of the pipe, you can put a metal piston and then haul a big-ass heavy weight, like 100 or 200 feet above that, and you let it go. And it goes bang, like a hammer. This is the hydraulic part. And that pressure gets transmitted by the water. At the end of the pipe, that water goes bang. And the force you hit the water with is hitting the rocks in the ground. The goal is to fracture the reservoir rock so that those bubbles will keep escaping out of the extraction wells. Every time you pick up the weight and let it go, it's like hitting it with a big old sledgehammer. So you hydraulically fracture the reservoir rock. Yes?
So like when you see liquid oil and stuff, it's a lot of just water.
I don't know when you're referring to this.
Like in movies and stuff, you see like oil bubbling up or on TV shows from the ground.
From fracking?
Well, so there are actual liquid oil deposits under the
Oh, yes.
ground.
Yes. Now you got to think about what that sand and chemicals are doing, though. Because remember that a lot of times if you just break up rocks, it's underground, right? So those rocks are just going to fall back in on themselves, aren't they? You know, imagine. If this door represents underground rock, the spring represents all the pressure underground. So if you use a hydraulic hammer to push that open, what's the pressure going to do? It's going to close it, right? But if you have little pieces of sand in the water, you get the hydraulic hammer effect carrying the sand. The sand is used to wedge the rocks apart when they fracture. Everybody got that?
It's so simple.
There are oils and soaps in the water to lubricate that sand. So on the next hammer stroke, this gets wedged open a little bit further by slightly more sand. Because, you know, when you're fracturing those rocks, there's a whole bunch of like thousands of feet of ground on top of that are trying to squeeze them back together. Unless you fracture them apart and then wedge some sand in there to keep the bubbles flowing. They use cool chemicals to make the rocks more slippery. They use other chemicals to make the rocks more brittle. They use other chemicals to make the natural gas extra fizzy. Like seltzer in water, to make little tiny itty bitty bubbles so that they'll rise more easily through the little cracks. So the chemicals in the sand help you deliver more gas out of the extraction wells. Does that make sense to everybody? One bit of good news, the United States has a tremendous volume of natural gas. You should Google this to find the right number, but there's much more energy potential in this natural gas than there has ever been in petroleum in this country. Much more. You can ask your Google machinery to give you the right numbers. But the number of natural gas energy potential in the United States is astronomically higher than the petroleum in place potential for the United States. Yes?
It's cleaner and abundant, but is it cheaper?
In many ways, yes, because once you have the infrastructure, it's a very light fuel. You know, if you're my end user over there in like South Dakota, and I'm the production well over here in Pennsylvania, I could keep buying trucks and paying truckers to ship it that way, and then we got to bring those truckers back with the empty tank, so I got to buy a round trip for a tank of petroleum, right? Or I can just build one big-ass pipeline. And it's a big, fancy pipeline. It takes a little maintenance. But once we have the pipeline, I just go on my side with a compressor, and at your end, you just go, thank you, and you open the faucet, flowing out. Pressurize it in one place, keep it airtight along the way, comes out under pressure at the other place. And if you want to extend that pipe all the way over there to Alaska, why not? Those pipelines are expensive, they're dangerous, they blow up sometimes, they get hit by trains and then they blow up sometimes, they get struck by lightning and then they blow up sometimes, they leak, and so there's technically a gajillion, trillion, zillion gallons of methane going into the atmosphere out of all those leaky pipes. But mechanically speaking, it's a really cheap fuel to deliver. It's very cheap to refine. And it's hyper abundant. I mean, there's a lot in these deposits. And you get a better percentage out than petroleum. Don't forget that in a deposit of petroleum, you're lucky to get anything over 40% of the petroleum out. Natural gas, you can get 70, 80, 90% extraction with fracking. Yeah.
So since you said that natural gas is like exponentially more than the petroleum potential,
Yeah.
since we are getting about 2% of the petroleum, is it anywhere near, are we getting the amount of petroleum from natural gas anywhere near what we got whenever we were just extracting petroleum?
Are we getting the amount of energy out of natural gas that we once did getting?
No, because you said because the natural gas potential is like exponentially higher than petroleum itself. Natural gas, we can get about 2% out of that anyway.
It's not that you get petroleum out of natural gas. It's that in wells where you frack, what comes out of the pipe is about 98% natural gas, and some of the wells will produce a little petroleum too.
Oh, okay. But that doesn't get anywhere near what we were getting here.
No, if it was a petroleum primary well, it would produce way more. That petroleum is often a waste product of the natural gas infrastructure, and it's so minute that it's not even worth packaging for sale and process. Yeah.
Is natural gas solely more abundant in the U.S. or Canadian?
No!
Yes, ma'am. So there would be enough to more than petroleum globally?
Oh yeah, oh yeah. And I've heard such conflicting astronomical numbers that I'm not sure if we're talking about the same thing. But I've heard people say there's like 2,000 times the energy potential in methane than there is in petroleum. And
so what's the tragic con of fracking? What's holding us back?
Yeah.
well, there's that.
Oh, I've seen videos of that.
So there are, yeah, that's a good slideshow, right? Pay you later, bro. Good job. Look, there's some serious problems with the fracking thing. It's kind of easy money, but it's kind of problematic. Conceptually, I got to make sure that everybody understands something. Natural gas is a gas, so it rises, right? There's something underground that's holding it underground, right? Do we agree? You know, the cap rock? We talked about that, right? Because without that, it would just, there's a lot of ground, wouldn't it? That cap rock, is it airtight? If it wasn't airtight, could it hold the gas? No. So it must be because it's holding a gas. So it has to be airtight. Do we agree? Because it's like an air barrier. And so groundwater can't get any deeper than that rock. Do we agree? If you have shallow natural gas, then you have cap rock. What's on top of the cap rock? Groundwater. Now, in some cases, you've got natural gas, cap rock, other rocks, more rock, bedrock, and then water. But either way, you got to first go through water, then go through some amount of rock to reach the gas. Everybody feeling me on that? And then you're going to start shattering the rocks. The potential is clearly there for one little crack that you did not intend, which allows cross-contamination of either fracking fluid in groundwater or groundwater trickling into your hydrocarbon deposit, or both. There's all these crazy stories coming out of like these places where people say like, oh, you know, like lightning struck and the ground caught on fire and it's been on fire for 6 months. Or like some poor farmer went into a shed and lit a cigarette and it went and his brother's like, we smoke every day and we've never blown ourselves up in the shed before. Maybe that's because my neighbor has a big old fracking thing now.
There's videos of people lighting their faucets.
Or you can Google tap water on fire and see like 38 million people in those red parts that can light their water on fire and like, our water wasn't flammable before they started fracking. Now all my neighbors have cancer and we can all light our water on fire since they started fracking. And you ask the natural gas companies and they're like, wasn't us. Everybody else is like, but bro, X then Y. But here's the big problem. All this stuff that happens underground stays underground. It's like Vegas. So like nobody knows what's going on down there because it's like 7,000 feet underground. And so if there's like a little seam of rock which comes out of Gabe's house, how is he going to prove, as Joe Schmo, public dude, random guy in the middle of Pennsylvania, that it's my fault, like 1 state line and 3 counties over? He's like, hey, wait, they're fracking over there somewhere. Yeah, fracking. Fracking. And then we, the natural gas companies, like, it's not my fracking fault. Maybe those hydrocarbons are just naturally present in his water. Maybe that's his neighbor's bad habits. And so there's this like really tangled web of, oh, and then there's what are called trade secrets. Where Gabe's like, yo dude, my water's flammable. And I'm like, not my fault. And he says, but there's all these weird chemicals in there. And I'm like, prove it. You can't prove that they're mine. And he says, well, just tell me which chemicals you're using. And I get to say, ha ha, trade secrets. So there's all this like secrecy and mystery about which chemicals are being used, and a lot of them haven't necessarily been tested for all their interactions with other chemicals in the ground, and all the different rocks, and the aging, and the hydrocarbons, and like, it's just getting really complicated is the bottom line. Because look, this is truly a gold rush, like lots and lots of economic potential. In a lot of communities that are economically quite depressed, and it's all new legislation. There are no standards for like how to do this. Most places haven't figured out how to regulate it. Some parts of the world are like, no, we're not going to do fracking until we figure it out. And other places are like, well, we're not going to stop making money until you prove us wrong. And there's a movie that I'll show in this classroom Tuesday and Wednesday nights at 6 p.m. called Gasland, award-winning documentary from 3 years ago, about all these complications in the rural communities where natural gas is both easy money and scary cancer agent. Yes, question?
So, a gas company cannot disclose what's in their chemicals because it's intellectual property, or they developed it?
And so there must be some way to force them legally,
Yeah.
I would think. But it probably doesn't end up in the LA Times.
No.
And so there's like difficult layers of secrecy that I assume at some legal extreme must have oversight. At least I hope that's true. But you know, these are like powerful big businesses doing cutting edge science, and like, it's like, I don't know what kind of chemicals are in my effing jacket, let alone what somebody's doing in Pennsylvania 7,000 feet underground. Yeah.
But does this happen? This happens in other parts of the world other than the US, right?
Yeah, some dude in Russia built the most wealth for a single human in the least amount of time ever. The fastest rate of wealth gain was the young Russian man who got control of that. Apparently very well educated, came from like a, you know, wealthy family, but we're talking like millions with an M. And the dude like comes out of college and he's all young and like, mommy, daddy, can you get me a meeting with so-and-so? And can you help me get this paper over to so-and-so? And then like in something like 15 years, the dude is like the third richest human on earth or something. You should Google him, Russian natural gas tycoon. He has like kind of a big media presence now, and he's like kind of an extravagant spender because he's a young dude, and like he got really rich really fast. I believe it is the most wealth gained by a single human in the least amount of time in the history of humans and money. Vertically integrated empire. So he got the land, and he bought the plumbing company, and then he bought the pipes, and then he bought the trucks, and then he bought the transportation infrastructure, and just went like top to bottom. And then I was like, whoa, this is like rocking it. Anybody else? Yeah, that laugh. Whoa. Okay, number 21. Number 21. Gabe, I'm sorry that you can't see from back there, but it can't be helping Julia that you're also talking at her the whole time. Gabe was arrested? Oh, the old tycoon was arrested? For what?
I'm driving drag racing
Yeah.
I didn't know Russia had police. Yeah, why
Now,
does everyone
students, this is number 21. I'm very frustrated right now. To the degree that I have stimulated your brains, I'm really glad. To the degree that this class starts to spiral into out-of-control mumblings, it's really frustrating. Remember, there's no prohibition on leaving the room. Take your conversations outside. You're welcome to have them. I'm not trying to keep you from your friends. Like right now, right there, you're welcome to do that outside. Just don't distract my students in here, please. Some kids are here to learn. Remember that whenever you find fossil fuels, there's always a blend of all of them. Traditionally, whenever we got down to the coal, we would have to deal with this methane, which was just like an impurity. Where's my sandwich?
Do you want one?
Yeah. And you know that. Yeah. ¿Se como? Hi. Thank you, thank you, thank you. Actually, can you please deliver these? They're right out there, right next to the door. William, raise your hand. Can you give us hands? You can have them both. Thank you. Thank you very much. Okay, back to me now. There's a bunch of methane mixed in with the coal. Back in the day, you would have to be very careful in a coal mine because there's all this methane and it can kill you because you get explosions in coal mines. Maybe you've heard about this. Globally, mining for coal is one of the most dangerous jobs on earth because coal mines explode all the time. And so some poor schmuck is down there digging the hole in the coal, and you make a spark, and then the methane that's mixed with the coal goes bang, and then you get a collapse, and then the schmuck is buried in what used to be a mine shaft. Is it true that schmuck means penis in Yiddish?
Probably, yeah.
Anybody know?
Yeah.
What? No?
Is Yiddish a real language? Yeah.
Go sit in the corner.
Where do they speak Yiddish?
Yidlin.
Yidlin?
Yeah, in Yidlin.
That's a fair question.
Isn't Yiddish like German Hebrew?
It's it is dialectic Hebrew, I believe. And I believe it is spoken by descendants of Hebrews and Hebrews in all the parts of the world where they are found. Which, given the diaspora, is kind of far-flung. Perhaps I shouldn't have said schmuck, or maybe I shouldn't have said penis, but back to me now, please. Really? So the bad news, of course, is that when you're going to pump water through a coal mine, you realize you're going to get some really nasty water out because you just pump water through a coal mine. And so you generate tremendous volumes of water pollution, really nasty water. So on the one hand, the methane is dangerous when it's in the ground. On the other hand, if you release it to the atmosphere, it causes a ton of global warming. Did you guys know that methane is 10 times hotter than CO2? Write that down, fun fact. So you can't just let it go up into the air because it's 10 times hotter than CO2. And you can't light it on fire at the coal mine because, you know, you can light all the coal on fire. And of course it's money, so it's tempting to turn the coal bed methane into money, but then you got to pump water into the coal bed, which means you get the slushy, nasty, hydrocarbon polluted wastewater, which is another nightmare. But now comes one of my favorite days of lecture, right? This is a cool little fact for science nerds unite. This moment rocks. Okay, science nerds. Which is Sam, apparently. Why is everyone laughing? Why does ice float in water? Less dense. It is less dense. Thank you. Okay, quit tracking Julia. Second of all, why is ice less dense than water?
Jesus.
In what? Thus, less dense, more dense. I mean, ice is made of water, so how can it be less dense than water? Because the water is arranged differently. Perhaps you've seen sometimes the two H's drawn on top of the O like Mickey Mouse ears. Anybody ever seen that? Where people will draw a water molecule like this. And maybe you've never seen that, I don't care. Now watch. When they are in liquid form, those water molecules can slide past each other any number of ways because they're in liquid form. They don't mind being close. But science nerds know that this is a polar molecule. The O side is slightly negative and the H side is slightly positive. So watch me. As a liquid, those things are pretty close. But when they want to line up and make a solid, they have to spread out. Making a hexagonal base structure like this, a crystalline latex matrix. Latex. I got latex on the brain. Okay. Yeah, that was kind of grisly. Sorry. Anyway, this this is an ice molecule. And you know, sometimes
That's cool.
when water is freezing into ice, you'll have little methanes around. And methane is a very, very small molecule. Relative to a water molecule, methane is tiny. Those hydrogens are really close to the carbon. They love each other. So methane is like about that size. And when the waters are getting into this shape, sometimes the methane is trapped in the middle, like that. It's not a bubble. Write that down. Not bubbles. The methane in ice, it's not like bubbles of gas in ice. It is molecules at the molecular level. The methane is just sort of trapped in between there. A single molecule for every like 18 or so water molecules. And there'll be another one over here, and another one over there, and another one over here. Because the methane is small enough to fit in between the bonds of the ice. But because of the polar nature of these things, it can't get out of that cage. Does that make sense?
So if you melt the ice, is the methane still?
Dude, every time you ask a question, pow! I got pictures for you. So there is some ice underground, and check out what happens with that ice. It's no joke.
Flammable ice. Is that what Eskimos use for fire?
Eskimo is a derogatory word.
Inuit.
Thank you. No, he did not. Check this out. You can even hold it, because it's still ice.
What?
So the methane burns, you know, they're not bubbles, it's at the molecular level. So as soon as the heat melts a little layer of water off the top, that water will literally pour out and the methane rises like the flames floating on top of a butane lighter.
So is that what is
I'm so glad that you're asking questions and everything, but seriously?
Is it frozen water or ice?
All ice does this?
That's all the question.
Oh my god. Kyla, you don't want to are you serious? Right.
Hey, that's cool, that's cool, that's cool, that's cool. So it is both flame and fire. And that ice, you know, you can shave it and make it into snow, and it looks like real snow, and you can pack it into snowballs and feed it to my daughter. No problem.
Light it
No
on fire.
problem.
Why do you not have that on your wall? That's excellent. She's so stoked.
Yeah.
If you eat the methane ice, will you burp methane and can you let your burp out?
I guess you could, yeah. We never tried it with her, but
Light your baby on fire.
that was just a joke. That's just a regular snowball. I went to Mammoth and I brought back a bucket of snow for my kid, and that night when I was looking at those pictures, I made the slideshow for the methane hydrate lecture 5 years ago. So that's just regular snow.
She's so stoked.
She's so cute. Do you see how big her eyes were? Yeah.
If you were going to melt that ice, how would you trap the methane?
And that's exactly the problem. As an energy source, there's really no viable way to trap the methane. I mean, you could just put all that ice in a container and let it melt, and then the methane would float and the liquid would sink. But it's still like 80% water, less than 20% methane. So this is not a viable energy source. I got to talk about the problem, and I only got about a minute and a half, so I hope you write down your question and ask me tomorrow. But look, there are ocean deposits. You got to know that. Any place that things decompose anaerobically and ice is forming, the methane will be trapped by the matrix of water. Any place that things are decomposing anaerobically. and it's cold enough, you make methane hydrate. Like the bottom of the ocean. Hold on a second, stop. And the permafrost in the Arctic deposits. When we come back tomorrow, I'll ask you if anybody can imagine the positive feedback of global warming with this.
Wait,